let's revisit the topics of underfitting and overfitting. As we've seen, we don't want our model to be underfitted, but we also don't want our model to be overfitted. Now, what did we do? What were some of the things that we did to tune our model, to figure out what's a good model to use, one that is neither underfitted or overfitted? What did we do? In those situations, we understood there are hyperparameters to the model. These are model parameters that are going to govern the learning process that are set prior to learning. And they're also going to control the amount of underfitting and overfitting we have for our model. So we performed a train test split. We applied cross-validation. So we used a tool something like Grid Search CV or Randomized Search CV. And we searched through a space of different hyperparameter values and different hyperparameters in general to figure out what's a good combination of hyperparameters such that I have a model that is hopefully not underfitted but also not overfitted. One of our goals is we want to have a general model, a model that is not too fitted to the training data, that hasn't memorized it, hasn't learned from the noise, but it's going to pick up the signal. But we also want a model that is adaptive enough to pick up all the signal that's in our data set. You can view error as having three components. We have bias, we have variance, and we have irreducible error. Irreducible error just corresponds to error that we cannot reduce. This comes from the fact that with data collection, there's always going to be some amount of noise, some amount of error that we will collect. And as the name suggests, we cannot reduce this error. So irreducible error, we won't talk about it anymore. For the most part, this error is composed of bias and variance. Bias deals with the constraint of the model from model assumptions. For example, in linear regression, there's a lot of assumptions that model makes. One of the key assumptions behind linear regression is that there's a linear relationship between what we're trying to predict and our features. Obviously, our features don't necessarily have to have a linear relationship. So that's a big assumption that's going to simplify this linear regression model. So a model that is underfitted is going to have high bias, as the model does not have sufficiently learned from the training data. And the reason why it's called bias, so one of the reasons why I like to visualize or think about why it's called bias, is because if someone is biased, then they have some preconceived, very simple notion of something. Let's say, for example, if I have to evaluate what type of chefs are better, and let's say I, for some reason, I have a prejudice, and I say all left-handed chefs are horrible. And for some reason I have that prejudice, and no matter what you show me, no matter the observations you show me of left-handed chefs that are pretty good at doing what they're doing, that's not going to change my mind. I'm not going to change my mind. I'm very biased. I have a very simple worldview that all left-handed chefs are horrible. It's a very simple thinking, so that's why you can consider why that's considered a biased model. So having a lot of bias in our model is going to correspond to a model that is underfitted. Now let's consider the other extreme. What if we have a model that is too adaptive, has a lot of bells and whistles, have a lot of capacity to adapt to the training data? Those models are going to have high variance error. So variance is going to deal with the model learning from the noise and the idiosyncrasies of the training set. And the more complex the models we have, the more vulnerable to variance it has, since there are more parameters that can adapt to the training data. So start memorizing the noise. And the reason why it's called high variance is because these model parameters are going to be highly variable given different instances of the training data. Those model parameters are unstable. In other words, if we train the model with a training set and we look at the model parameters and we retrain it with a different training set, of course we expect the model parameters to be different, but if they're considerably different, if they're highly variable, that's an indication that we have a model with a high variance error. Those model parameters are highly variable, and they're highly variable because they're too dependent on the exact training data we gave it. So it starts to not only learn from the noise, but starts memorizing the observations. It starts matching the noise that's in our data. We don't want that. So going back to summarize, oftentimes this is called bias and variance, the bias-variance trade-off. Underfitted model is high bias, and an overfitted model has high variance error. And that's why it's crucial when we start talking about these machine learning models that we discuss the hyperparameters that are involved in these models. What bells and whistles, what knobs, what controls do we have to our disposal to get the most out of our model, to properly tune the model to our data set such that it can be as general as possible, that is not overfitted, and hopefully as well as not is not underfitted. Remember, we want our model to do a good job on making predictions on data it has not seen, data it has not learned from. Now, one of the questions might arise is, well, we have a model. How do we get a measure for the amount of variance and bias we have in our model? So I'm going to talk about this. I'm going to go ahead and do some coding here, some live coding, to demonstrate some purposes, some of these ways we can diagnose our model. So let's say I'm gonna import, let's say import my data set. So I can import the California data set. Import model selection, import train test split. Remember, I'm doing this train test split to properly tune the model. I'm going to train on the train and evaluate on the test. Okay. Let me import matplotlib for plotting purposes. All right. So let's go ahead and train a simple model. So I'm going to say let's train a decision tree model. Import decision tree regressor. And I'm going to set the max step. I'm going to set it to a value of 2. Okay, so let's go ahead and train it. I'm not going to tune it. I'm just going to train it with this max depth. Of course, in real life, I would tune great max depth value, but see how well it does here. So I'm going to evaluate on the test set. So let's see how well it performs. So I'm also going to print out several things here. The training R squared. And the testing. Okay, so this is our results here. So notice that the R-squared value is better for the training set. Does that make sense? Is that intuitive? Generally speaking, what's going to happen is that the model will have a lower error on the training data, or a better performance metric. So we see here that the R-squared value, which we want as high as possible, close to 1 as possible, is higher for the training data as opposed to testing data, which makes sense because the training data are the ones where it learned from, are the observations it saw and learned and ingested from, try to find the patterns. So it makes sense it would do better on the training data as opposed to the test set. Now we can get a measure of bias by how much this model deviates from a perfect model. So the perfect model will have an R-squared value of 1. So notice there's a large deviation between 1 and 0.42 on the testing set. So that large deviation means in general we have a model that's underfitted. And notice the deviation, what I want to point out, the deviation between the training and testing set. Ideally, our model will have the testing error and the training error are very close to each other. That should be the ideal situation. Obviously, that's not always going to happen. There'll be some differences, but the larger that deviation is from the training and testing is going to suggest greater amount of variance. Because let's examine what variance represents. Variance means that the model is started learning from the noise of the training data. It's too dependent on the training data. And we get a measure of that by seeing, let's see how it works with the training data. Let's see how it performs on it, on the training data. See how it performs on the testing data set, and measure that deviation. If there's a very small deviation in its performance between the training and testing, well, that suggests that it didn't really pick up that much noise. It didn't learn that much noise in the training data. So that's good, at least in terms of the model has low variance. But there's a big disparity between training and testing. Well, that means that the model was learning a little too much from the training data. It's picking up noise. And that translated by a poor performance with the testing set. So in this example here, in general, we have a model that has a lot of bias. So we can go ahead and increase the max step, which is increase the model parameters. So it's going to increase how well this model can adapt to the data. So I'm going to crank it up to 5. And there you go. So we cranked it up to 5. And notice that the deviation between a perfect model and the testing error has shrunk. We still have some deviation with the training and testing set. So we can do a better job with tuning this model. Now I won't go into tuning this model with something like grid search or randomized search. You can go ahead and play around with that. Notice you can always tune more than just one hyperparameter. You can use max step, min sample split, a combination of those to have a model that has very little deviation between the testing and training. So one of the questions that you might come up with is, okay, so let's say my model isn't doing so well and I want to get better performance. You might want to ask, is it worth it? Is it worth collecting more data? Because we understand that giving more observations to our model is going to help it learn patterns, pick up structure that can exploit for making predictions. But before we go out and collect more data, let's see if adding more data will really help out our model. Because we don't want to have a situation where we spend all this money and time and effort collecting more data. Collecting more data is easier said than done. And then we incorporate more data into our analysis and we realize, well, the model doesn't do that much better. So we just wasted all this time, effort, and money just to get a very small performance. I could have spent time doing something else. So let's see how we can go ahead and figure out whether our model needs more data. Now my question I'm going to pose to you here is, let's say we have a model that has a high amount of bias. It's underfitted. Do you think it will benefit from giving more observations? Or do you think if we have a high variance model on the other hand, on the other spectrum, do you think that will benefit from more observations? What are your thoughts? A model that is too simple is not going to make use of additional observations. It is rather simple. It's high bias. It's not going to really utilize those new patterns that might exist in the new observations. It's not very adaptive. So it can't make use of any additional patterns that it can exploit. It's just too simple. On the other hand, if our model is too adaptive, then adding more observations might help out the model's performance. The model is adapted enough to pick up those new patterns, pick up those new structures that it can use to increase the model's performance. Now let's see if we can visualize if adding more data is going to increase the performance of our model. So what we're going to go ahead and do here is generate what are called learning curves. So what I'm going to do here is I'm going to generate my model, my regressor, just a decision tree. I'm going to say a max depth of 3. I'm going to create a list here called error from the testing set, and I'm also going to call one from the training set. Now before we start calculating things out and generating plots, let's consider what we should expect. Do you expect, I guess my question is, if we have on one axis, let's see here, we have on one axis is the size of the training data, the size of training. And here we have some metric of error. In general, how should this curve look like if I increase my size of my training set? How should the testing error look like as I increase the amount of observations I have in my data set? We should expect something like this, roughly speaking. As you increase the size of your training data, the error will drop, the testing error will drop, but after some point it will plateau. Now it's a little hard to figure out at what point it's been plateauing, where it's plateaued, so it'd be nice if we can generate some upper bound or some lower bound, some measure of this lower bound. So what we can do here is so this right here, if I want to indicate, this is the error of our test set. But let's go ahead and plot an error curve, but the error of the training data. How would you think that curve would look like? How will our training error be a function of the training size? Well, let's consider, what do you think would be the training error if we only have one or two observations? Our training set is very small, just two observations. You think it will have a very large training error or a very small training error? If there's only two observations, then it's really easy to train a model that does perfect or near perfect on the training data. So as our training set is small, our training error is small. But as we increase the number of observations, then our training error will increase. But it will also reach a plateau. So we have something like this. And this is important here because, as we discussed before in the beginning of this lecture series, or this lecture here, this video, we said that in generally speaking, our training error will always be less than our test error. I mean, that conceptually makes sense. Yes, there might be some weird occurrences where it just so happens that the test error is smaller than the training error, but for the most part, what's going to happen is the training error will be less than the testing error, which makes sense because the training data, the training error, is the error it incurred with the observations it learned from, the observations it saw the answer to. So it should do better on that set than the testing set. So we generate these two curves, we know that they will not intersect. And they will form some limit. They will indicate the limit. And we can use this as a guide to tell us whether injecting more observations into our analysis is going to help us out. If we have this amount of data, whatever this number is, then this is telling me that, you know what, adding more data isn't going to really improve the model's performance. But if I had this amount of observations, there's a large deviation between training and test. Large amount of a variance. Large amount of deviation between testing and training. Oh, I would benefit with increase the number of observations if I collect more data. So I might need to talk to people and say, okay, it looks like I should collect more data, or adding more data is helpful. Let's go about and generate more data. So you can use these training curves as a guide to figure out what is your next approach to getting the most out of your model. Of course, you can always add additional features to help out the model. But the point here is, before you do something expensive, and expensive both in time, resources, and in money, then you should consider, well, is adding more data really helpful? Perhaps I can do something that's less expensive, like playing around with feature generations, retuning my model, things like that, to get the most out of my analysis.